Hiya folks, in this video we're going to try and summarise as much as we can of the topic of capacitors and fit it all onto one page. So let's start off by having a look at what a capacitor actually is. So a capacitor is a component that's able to store charge in an electric field that exists between a pair of metal plates. So these parallel metal plates are usually made of foil and they're separated by an insulator such as plastic or wax paper. Now usually then it would get rolled up into the component. So the symbol that we use to show a capacitor in a circuit shows that it is made up of two parallel plates. Now one of these plates will have a positive charge and one of these plates will have a negative charge. And between those plates we have a uniform electric field. So the field lines we're drawing here are equally spaced and parallel to each other. The electric field is acting in the direction of positive to negative, because if we were to place a positive charge in the middle there, it would be attracted towards the negative plate and repelled from the positive plate. So to understand how a capacitor works, we need to think about electron flow and how electrons move within a circuit. Usually when we talk about electrical circuits, we talk about conventional current and how it goes from positive to negative. However, in reality, it's the electrons that are moving and they're going from negative to positive. So let's imagine that at this point here, we have an electron, which is negatively charged, and it's right beside the negative terminal of the cell. Well, those two negative charges are going to repel each other. And so that electron is going to move away from that negative terminal, and then it is going to make its way towards this first plate. Now remember that this plate is separated from the second by an insulator, so the electrons can't travel across. And what happens here then is that they gather on this plate. It has an excess of electrons, which means it's negatively charged. Now at the same time on the other side, an electron on the other side of that capacitor will now be repelled from the excess of electrons that we have in the first plate and also be attracted towards the positive terminal of the cell, which means that our second plate here is now going to have a deficit of electrons, meaning that it's positively charged. So it's important that you can figure out which side of the capacitor is positive and which side is negative. So a capacitor's ability to store charge is what we call capacitance. So capacitance is defined as the charge stored per unit of potential difference between the plates. So we're able to write that as an equation where we use the symbol C for the capacitance, capital C, is equal to the charge that is stored, we use a capital letter Q for the charge, divided by V for the potential difference. Now we measure this capacitance in farads, and normally the value for capacitance will be quite small, so make sure that you're familiar with all your prefixes. When a capacitor is charged, work is done in moving those charges in order to get them onto the plate. As the electrons are building up on the negative plate, the bigger the charge that's on the plate, the harder it's going to be to get more electrons on it, because there's going to be more repulsion happening there. So work is done to overcome that and get the electrons to stay on the plate. So we met the equation for work done in a circuit, in an electrical sense, back in year 13, and we find that work done was equal to Q times V. So that's the charge times the voltage. Now if we were to plot the charge against the voltage, what we would find is that the more charge we have on the plates, then the more voltage we have. And from this we can actually find the work done, find the energy stored in a capacitor by determining the area that's under that graph. Now you'll see that that shape is a triangle. So work done in a capacitor is actually a half times the charge times the voltage. Now there's a few other ways that we might work that out. If we use the equation we made above, that the capacitance is equal to the charge over voltage, I could rearrange that so that we have charge is equal to capacitance times voltage and put that into the equation. So work done is equal to a half times the charge, but instead of writing charge, I'm going to write CV. So times C times V multiplied by the V that we already had, which means that the work done is equal to a half times the capacitance times the voltage squared. We could also rearrange the equation for V instead and say that V is equal to Q over C, charge over capacitance. Well then that will have the effect of changing our equation to a half times the charge times Q over C, and that leaves us with a half Q squared over C. So 3 variations then of the equation of finding out the energy that's stored within a capacitor. Next we're going to have a look at how we work out the total capacitance if we have multiple capacitors arranged either in series or in parallel. So let's start off and look at the capacitors in series. So here we have 3 capacitors in series and I've just labelled them C1, C2 and C3. Well, in any series circuit, we know that the energy or the voltage is going to be shared out between those different components. So that actually means that the total voltage across these 3 capacitors would be equal to the voltage across the first, plus the voltage across the second, plus the voltage across the third. Now, since the voltage is equal to Q over C, which we met earlier, we can rewrite this equation as QT over CT, so that's the total charge over the total capacitance, is equal to Q1 over C1 plus Q2 over C2 plus Q3 over C3. Now this is a series circuit, which we should know from year 13 and from year 12, that in a series circuit the current is the same everywhere. Now current is the flow of charge, so if the current is the same across all 3 components, then that means the charge is the same across all 3 components. So actually all these values of Q are the same, which means we can cancel them out. And the result is that we have 1 over CT, C total, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And you'll notice that that is very similar to the equation that we would have met for resistors, except this can be likened to the equation for resistors in parallel, where we're using 1 over. And that equation will work for any number of capacitors that you have. So now we'll have a look at the parallel network of capacitors. So in a parallel circuit, we know that the voltage will be the same across each component, but the current will split and will be shared amongst the different components. So if the current is shared across the components, that means the charge is shared across the components. So we can say that the total charge is equal to the charge across the first capacitor plus the charge across the second plus the charge across the third. Now, since that charge is equal to the voltage times the capacitance, then we can say that we have the total voltage times the total capacitance is equal to the voltage across C1 times C1 plus V2 C2 plus V3 C3. Now again, we mentioned this already, but since this is a parallel network, the voltage across each branch is the same, which means all these values of the voltage are identical and therefore we can cancel them out. So what we're left with is 4 capacitors that are in parallel. the total capacitance is equal to the sum of the individual capacitors. And again, that will also work for any number of capacitors that you have. Okay, so now we're going to have a look at charging a capacitor. In order to charge our capacitor, what we do is connect it to a battery or a cell. Now remember that it's the electron movement repelling from the negative terminal and going towards the capacitor means that this first plate will be negative and the other plate then will be positive. That will keep on happening, it will keep on charging, and those charges will continue to move and gather on the plate until the voltage across the plates of the capacitor is equal to the EMF of the cell or of the battery. We can control how quickly that capacitor is charged by putting a resistor into the circuit. If there's no resistor, it will happen almost instantaneously, but if we do put a resistor in, the bigger that resistor is, then the longer it's going to take for the capacitor to become fully charged. So we describe this as an RC circuit. What we find is if we have a very small resistance, then the voltage across the capacitor will increase sharply at the beginning, and then it will start to level out until it reaches a maximum value. Now that maximum value here is equal to the EMF of the cell. If, however, we increase that resistance, then that's going to slow down the rate at which the capacitor reaches that maximum potential difference. So the graph will look something more like this. When it comes to the current, when we're charging a capacitor, what we find is that initially there is a large current, there is a large flow of charge. However, as more and more charge builds up on the plates, it becomes increasingly difficult to get the charges onto the plate, and therefore the rate at which those charges move slows down. So what we find is that we have an exponential decrease for the current as it's charging, and that would be for a small resistance. If we have a large resistor in place, then that's just going to again take a little bit more time for it to charge, but the rate at which it slows down will also decrease. So it's going to look something more like that. Okay, so next we'll have a look at discharging the capacitor. So in order to discharge a capacitor, all we really need to do is to provide a route for the electrons to get off of the negative plate and back to the positive plate. So if we connect a wire across the ends of the capacitor, that would be enough to discharge it, and that would happen almost instantaneously. If we put a resistor into that circuit, then that's going to slow down the rate at which the capacitor discharges. So these electrons are going to move away from that negative plate, and they're going to move around the circuit towards the positive plate until the distribution of charge is even once again. We could also take the charged capacitor that we had to begin with and then connect across it in parallel, connect an uncharged capacitor. So these two are connected in parallel. What's going to happen here is electrons are going to move from that negative plate towards the capacitor here at the bottom, and they're going to gather on this first plate, which means this plate will also become negatively charged and the other side will be positively charged. And that will continue to happen until there is no potential difference between the two plates. If we measure the voltage across the capacitor as we're discharging that capacitor, we find that there is an exponential decay relationship between those. And the graph against voltage against time would look something like this. The same is actually true if we were to plot the current against the time. We would also get this same type of curve, and that's true as well for charge. So we can formalize that shape of graph with an equation. We can say that the voltage at any point is equal to the voltage at the beginning, which is V0, multiplied by e to the power of minus t, being the time, divided by tau, which is the time constant. So we'll have a little look at that in just a second. The equation is actually the same for current and for charge. So the time constant is the time that it takes for the current to reduce down to 37% of its initial value. In fact, it could be the time taken for the voltage or charge also to reduce down to 37% of its initial value. So the symbol in the equation that we use for that is we have the Greek letter tau, which represents our time constant, and that is equal to the product of the resistance and the capacitance. So you could see these previous equations written with RC instead of tau. Tau is a time constant and it is measured in seconds. So you might need to describe an experiment in how you would actually determine this time constant. So you would need to be able to recall what the experimental setup is, to be able to draw the diagram, what kind of measurements you would take, how you get your results from that setup, and then how you would manipulate the data you've collected in order to obtain the time constant. So the circuit that we have drawn here, you need to be able to draw. The circuit allows for this capacitor to be charged and then discharged. So whenever the switch is in the up position, then it is connected to the battery and it is allowed to charge. That will happen pretty quickly because there is no extra resistance in that circuit. So almost instantaneously the capacitor will charge. Then that switch is put into the down position so that it's disconnected from the battery and now it's connected across the resistor and it will start to discharge. So it's also connected with an ammeter in that circuit so that the ammeter can record the current as it is discharging. That will happen over a period of time. It won't happen instantaneously because there is a resistor here in the circuit. So the measurement required would be the time, and we measure the time using a stopwatch, and we measure the current by using an ammeter or a multimeter. We charge the capacitor fully to begin with, then change the switch in order to discharge that capacitor and start the timer at that exact same time. We record the current then at regular time intervals. So we'll get a view then of what happens to the current with time as the capacitor discharges. We take that data and then we plot it on a graph of time on the x-axis and then current on the y-axis. What we'll get is that exponential decay curve. And in order to determine what the time constant is, we need to first read off what the initial value of the current is, which we call I0, and then we need to find 37% of that initial value. You then use a ruler, draw a line across from that value of the current until it meets the curve, and then drop that line straight down, and you read off that value for the time. And that value is the time constant. It's also really good practice to repeat that a number of times from your graph. So you should try your best to get 3 results and then take an average. Doing these decay curves can be quite tricky. It's really difficult to get that smooth curve. So a much better approach would be to plot this as a straight line. So if we look at the equation, where the equation is I is equal to I0 e to the minus t over tau over the time constant, what we could do is take in the natural logs of both sides. So that's ln. What we'll end up with is the natural log of I is equal to the natural log of I naught plus the natural log of e to the minus t over tau. Now, taking the natural log of e cancels it out. So what we've actually got here is just the minus t over tau. So I'm going to rewrite that as minus t over tau. Now I'll rewrite that in order to help it fit in with the standard equation for a straight line, which is y equals mx plus c. So we could write this as ln of I is equal to minus 1 over tau, that's the time constant, times t plus ln of I naught. And if I just put the equation for a straight line below it, then what we'll see is if we were to plot a graph where we put the natural log of I on the y-axis against the time on the x-axis, then we will get a straight line, and we would expect a straight line with a negative gradient because of the minus here. And so the gradient then would equal minus 1 over tau. Finally then, just be aware of some of the uses of capacitors. So some of the uses that might come up in your questions for capacitors are a flash gun. So capacitors discharge really quickly through a gas-filled tube, and that produces a really intense flash of light for a very brief period of time. And that could be used, for example, say in a camera, the flash in a camera. Another example would be using a capacitor in a defibrillator. So here the capacitor discharges again very rapidly, but the aim of this one is to deliver a controlled shock to the patient's heart. And that is given whenever a patient maybe is having a heart attack, or they're having what's called ventricular fibrillation. So the heart is beating very fast and not in a coordinated way. Well, then delivering this shock can stop that irregular beat and get the heart to resume the normal rhythm. So that is capacitors then, well, as much as we can fit here on one page. Hopefully you found some of that useful. The best thing for you to do next would be to start looking through some past paper questions and trying out these calculations. There'll be some videos coming up here working through some examples which you might also find useful.